Hi, Professor. Didn't forget to do that. Then, we have had a lot of ficas, which means coffee, with him at university. Just a short bio, because he's a big shot in physics. So it's just to tell you, he graduated in 1994 from Constance University in Germany. Then he did his PhD at Uppsala University in Sweden, nearby Stockholm, in 2003, where he got his degree. Then he went as a postdoc to Oxford University from 2003 to 2005. And finally, he went back to Gothenburg University in 2014, where that time he's now a full professor. He has a big lab, as you will see in his presentation today, the experimental results he does. And we are lucky enough to have him here because he is one of the last visitors I will have from the Linnaeus Palmi program. That is the one that University of Mexico, UNAM, and the University of Gothenburg are sharing for the last 8 years. Hopefully, if the war in Ukraine finishes soon, we will have the program renewed. We don't know, but that's a short bio. He will talk to us about the electron emission of quantum systems in complete and time-resolved fashion. Thank you very much for accepting the invitation. Welcome.
Thank you very much. Oh, yeah, that's much better, isn't it? Yeah, so once again, thank you very much, Remy, for your very kind introduction. It's a great honor to be here. I don't think I'm a big shot in physics. I try to do some things, and I will try to walk you through a few things which I came across. 94 is, in fact, when I left Constance and as a half-finished undergraduate. So the second half was done in Sweden, but still I got a German degree at the end because I wanted to have one. But then eventually I was always lucky in my career to meet nice and supportive people. And at that time I met the person in Uppsala who was very enthusiastic about something, which turned out, I didn't know that at the time when I went there. I learned it turned out to be the big thing in Uppsala, and this is photoelectron spectroscopy. So this is how I grew into that field. As a totally innocent student coming for a half a year, supposed to be half a year in Sweden. And it turned out to become more than half of my life, in fact, okay? So anyway, and this is also basically the topic is when we talk about photoelectron spectroscopy is photo emission. And I like to introduce this, now it's moving. Well, this is a little bit of a history. I like to do that in the beginning, but then I will fairly quickly move on to introduce you to a concept which I was learning then during my postdoc at Oxford with another fantastic person who was very supportive. And I, in fact, inherited apparatus from his lab because by the time I left, he retired, which has been an enormous thing for starting my own career. I eventually started experiments at the free electron lasers. I would try to touch one of those experiments, and then I will talk about this new laser lab. And it is, in fact, it is a big lab, which is on the way. I think many of you know this. This is how photoionization starts, Heinrich Hertz, right? This experiment, he casted light onto a surface, and then depending on the wavelength of the light, he could measure a current, photocurrent. And then, of course, he couldn't explain it theoretically. There was another person important for doing this. We all know that it's Albert Einstein. It's just a reminder about the photoelectric law, which basically tells us that if we know the photon energy well defined and we can measure the kinetic energy of the electron which is thrown off, then we can get actually hold of the ionization potential, the binding energy of the system. Then at the time, this is 1905, it took about 50 years until the first photoelectron spectrometer was made. And this was made by someone in Uppsala. His name is Kai Siegban. And there are different ways on how to can measure the kinetic energy of electrons. But Siegmann was an engineer by training, so he loved to build perfect instruments. So he very early on came up with this idea to use what is called a hemispherical analyzer. So the two hemispheres, and then you put across a certain voltage, the minus on the outer wall, on the outer hemisphere, the plus on the inner hemisphere. Then, depending basically on the voltage across those spheres in relation to the kinetic energy of the electron may reach or may not reach the detector. And then what you do is you add here a lens system, and basically scan through a kinetic energy range of the electrons. In this way, you then get a spectrum, which is basically then an energy scale and the number of electrons detected per for a certain energy. This gave him eventually the Nobel Prize, 1981. This is one of the 3 Swedish Nobel Prizes in physics. There are not so many, but it turns out he was the second one. The first one was his father. It's always an interesting thing, right? When the Nobel Prizes go within the family, basically. But anyway, I think it's a well-deserved Nobel Prize because it is the basic idea is it's electron spectroscopy for chemical analysis, and I will tell you in a minute why this is so good for chemical analysis. Of course, NMR was around already at the time, so this is a sort of complementary tool. Now the reason is, I should have taken this slide there. If we start off with an atom in the neutral ground state, and then you come in with a photon, depending on the photon energy, you may either take out an electron from an outer shell, it's then called valence ionization, or you take it from an inner shell, then it's called core ionization. And the core levels, they are the fingerprints for the individual atoms. And that was eventually what Siegmann realized by doing this photoelectron spectroscopy on a molecule like this, where there are 4 different atoms, but which have different chemical environments. They could actually show that those 4 chemically different carbon atoms, they have also different binding energies, if you have a sufficient liquid spectrometer to resolve that. This is why and it was of course not only him, he was operating large groups, so it's a real team effort. Now, the point is now, oops, wait, I don't want to destroy this. If we have created an inner shell, the system will not stay forever with an inner shell vacancy. It wants to go into an energetically lower condition. And this can happen then, what happens is that an outer electron will fill the inner shell, and then the energy which gets released in this way, that may be transferred onto a second electron. And that was discovered by Pierre Rocher. So this is what is known as the Auger decay. And then you can, of course, also with Siegmann's technique, you can measure the kinetic energy of the Auger electron, but it's not possible with his technique to measure the photoelectron and the Auger electron together and get their energy correlation. And this eventually, I want to show first another slide, but this brought me then to Oxford University, where I was able then to learn about how to actually measure the energy correlation of 2 or more electrons. So this is just like the first thing one needs to do is to extend the photoelectric law quite straightforwardly. I mean, it's still, you use a monochromatic photon energy, and then you want to have a technique where you can measure the kinetic energy of several electrons coming from this one and the same atom. And then you can write this equation, and then on the right-hand side, you can sum up the binding energies of those individual electrons, and then you will get something which we then call the double ionization energy. So what you then get is actually the electronic structure of systems which have lost not only 1 electron, but 2 or more electrons. And one can say, okay, how important is that? It turns out if you go on with the Auger decay, not only 1 Auger electron may come out upon creation of an inner shell vacancy, you may have 2 Auger electrons, then we call it a double Auger decay. And you can have 3 Auger cascades. They were, of course, already known from Auger's work, but they weren't really be able to quantify how much, for instance, the double Auger decay is relative to the total amount of ionization. And a few years ago, I had a PhD student who was interested in that, and we did this for a large number of molecules. Then we actually saw there is a linear trend, which is clearly correlated to the number of valence electrons of the atom bearing the initial core hole and the nearest neighboring atoms. And there we said basically, you know, that we mean the neighboring atoms which are within a distance of less than 2 angstroms. And from there we get a nice linear trend, which is in this paper, and there is an equation also. And for some of the systems, we found that, for instance, the double Auger decay is on the order of 30%. So it's substantial. There are papers in the literature where people always say those double Auger decays and triple Auger decays and so on, they are negligible. But if it's on the order of 30%, I would be careful, right? Okay, so this very similar story on triple Auger and so on. Now I will tell you how we measure that experimentally. And I like to go back to this simple picture, which I had in the beginning. So photon basically impinging on, now it's again a surface, but in fact, we do this on 3 atoms and molecules. And then let's say the photon gets absorbed by an atom in that surface and emits 2 electrons. Now, how can we measure the kinetic energy of the 2 electrons coming from one and the same ionization event, and also at the end of the day, make sure that they are actually from one and the same atomic species there. And the way is to go to an alternative method, how to measure the kinetic energy of electrons. We can use a time of flight method, which means you measure the time it takes for the electrons once they are born here, how long it takes for them to reach a detector, which is at a certain distance, right? Now, you want to do this very efficiently. And it turns out there are different types of time of flight spectrometer known. And it was already also a certain type known at the beginning of 2000. It's called a magnetic bottle electron spectrometer, originally invented by Frank Reed in Manchester and Peter Groot I think in Amsterdam at the time. But then that person here who was, and we're still working together, he was my postdoc advisor. He had the great idea to use that spectrometer in order to measure not only a single electron, but several electrons and get their energy correlation. And the way it works is you need to use a pulsed light source. So you have a radiation pulse, you create the electrons, and then you make sure that all the electrons born by this radiation pulse, they are pushed into a long flight tube. And in order to focus the electrons into this long flight tube, you use a strong permanent magnet. This is why it's called a magnetic bottle. There is a solenoid around this flight tube, which guides then the electrons to this detector. And then you measure how long it takes from the light pulse having induced the ionization until the electrons have arrived at the detector. You use, this is basically, this is classical mechanics. You use this relation, kinetic energy, basically the flight distance goes into, then you get the time of flight. Okay, and the deal is that you have a detection window open for a certain time, and then you look at how many particles arrive from the start. The light pulse start is the start, and then you keep the window open and see how many electrons do arrive, and from there you get their energy and so on. So John Eland was one of those, is one of those persons who can do experiments with very limited resources. So the first light source which he built at home was actually, it's called the helium gas discharge unit. That was the very first thing. And then eventually there is a French group in Paris. They started to do experiments at synchron radiation. And then I started to do the same. And I went then on to the free electron lasers with that technique. And now more recently, we also do experiments with femtosecond lasers, and I give strong support at the moment at the Lund Laser Center, where they use high harmonics to do attosecond science. And we set up another lab at the moment in Gothenburg, together with the Lund Laser Center in Sweden, where we also will want to do, and I'm pretty sure we will very soon do attosecond experiments there. So in fact, this is a family of spectrometers which we got. This is our workhorse, which we use at synchrotron radiation facilities. It's also the instrument which I built together with John Eland, which I then inherited. We built one for the linear coherent light source at Stanford. where I started the FEL experiments, but now this is actually at the Lund Laser Center, this instrument. I built a third instrument for another free electron laser called Fermi, and it can go to the LCLS if needed. And then we have another one. This is the longest one which we've got. It's 5.6 meter long. The others are 2 meter instruments, 5.6 meter. This we will use in our laser lab in Gothenburg, and we are actually putting together a second one now, and I will explain you in a few minutes why we need to have another one. So at the end, there should be 5. It's a family of spectrometers. And of course, I'm not able to operate them all by myself. So this is those are very interested. There are many collaborators that are interested in using those spectrometers together with us, and we give support. And this is it's a very good way of working together, actually. So now I want to just show you the beauty of this Eland coincidence technique. We say we have a double ionization event, xenon. We remove 2 electrons. Now we have a time of flight technique. And then nominally, we can plot the arrival time of the first electron on the detector versus the arrival time of the second electron on the detector. And if those 2 electrons come from one and the same atom, they will by nature end up on those hyperbolas. It's actually only both halves contain the same information. It's just like it's nicer to display it in this way. And then you convert it from the flight time scale to the energy scale by this the inverse of the root of the kinetic energy, and this gives you straight diagonal lines. And if you then sum up the intensities along those straight diagonal lines, you can have a spectrum. There are peaks, and what those peaks actually show us, those are the electronic states of doubly ionized xenon atoms. So this is basically the electronic structure of the dication, measured in a, I think, in a very nice and in a very beautiful way. That was what Eland had just achieved at the time when I came to Oxford as a postdoc. So now, but there is more to it. And I want to show you, you can plot this then in a 3-dimensional way. Now it's slightly rearranged. On this axis here, we take the energy sum of the 2 electrons related to the photon energy. It's called a double ionization energy. So then you have along those lines, you have basically the information on the dicationic electronic states. And then we plot here on the other axis, the kinetic energy of one of the 2 electrons. And from this, we can then see how those states are formed. And you see there is clearly a continuous contribution, but also there are discrete structures. And this tells us that the double ionization in a system like xenon atom can happen actually in 2 different ways. Either the 2 electrons are blown off directly, and then they can share the kinetic energy continuously. This gives rise to this sort of continuous background here. Or they come off in a sequential process. One goes out, leaves the singly ionized xenon atom in an excited state. This excited state decays, and a second electron comes out basically in form of autoionization, we would call it. And this is what you can get then for instance, xenon, but for many, many other systems. And I think this is really the beauty of this technique. You can then, when it comes to the direct double ionization, you can actually analyze how this energy sharing looks like for the 2 electrons as a function of the excess energy given to the electrons. So these are experiments done at a synchrotron. And there are those who are a bit more into it, they may know that there are basically 2 direct mechanisms which are discussed in the literature. One is called knockout, and the other one is shake-off. And then I had another student who actually invented the parametrization, how to get, how to get the ratio of those 2 processes as a function of the excess energies there. Now, of course, this is not only possible on atoms, and John Eland is a chemist by training, and his main interest is in molecules. And when I started to work with him, we did a lot of experiments on simple molecules and look at the electronic structure. And then this eventually led to a book, which we published it came out by the end of 2017. So in this book, if you're interested in the electronic structure of fairly small molecules, those which are easily accessible in form of gas bottles or run off the vapor pressure of liquids, then you will be able to find those spectra in that book. But then there is something else, which is, of course, happening to molecules when you remove one charge already, or if you remove 2 charges or more, then of course the system gets more and more highly charged, and it will start to fragment. There will be dissociation dynamics. What you then want to do is, you want to be able to get the full picture. And this was actually then what basically my postdoc was about. We wanted also to add on ion detection. And the way to do it is to replace, one way to do it, there are several ways. We have several ways shown how to do it. The original way is by replacing this strong magnet by a hollow magnet. And then we let the electrons go down the fly tube, as I discussed before. And then after a few hundred nanoseconds, we apply a high voltage pulse and push the ions in the other direction. And this basically gives you then there's an example of it. So CS2, doubly ionized, or wait a second, doubly ionized CS2. This is what we call the electron-only spectrum. It's hard to see, but it's highly structured. But sorry for the small scales here. And then what we show below here is actually how this electron-only double ionization spectrum of CS2, how it decomposes into the different sorts of charged particles created, the ions. So this is the parent ion down here, and then you clearly see that the lower part of the dication spectrum, there the electronic states, they basically belong to the stable parent, doubly charged parent ion. Then if you go higher up, you get the fragmentation, the different sorts of fragmentation. Now there is one very interesting fragmentation channel. This leads to C++ S2+. If you think about a CS2 molecule, the carbon atom is in the center, and then you have the sulfurs out there. How do you get to, when it dissociates, to something where the two sulfur atoms form an S2+ species? Okay, so this is interesting. For this case, we haven't actually got the explanation, but we have another case which is done on SO2. So there the sulfur atom is in the middle, and then you have two oxygen atoms out there. They do the double ionization, and you find again, if you look at it, this channel, which is O+, so the molecular O++ a sulfur atom. And there again, you have the same sort of effect. Somehow the two oxygen atoms need to come together. And this was then eventually explained because of the pandemic. I had a visiting professor at the time from Paris, Majdi Hochlaf, who is a theoretician. And he's very good in doing the sorts of calculations on the electronic structure and the dynamics of doubly charged systems. And to make a long story short, what he found by calculating all the potential energy surfaces and look at, so you know, he's using these methods like the complete active space self-consistent field method, together with a multi-reference configuration interaction, calculates the total energy for specific geometries, and then one needs to vary here both the angle of the sulfur atom relative to the two oxygen atoms and the distance, so what at the end, what he comes up with this concept of minimum energy paths is that if you analyze it, then you will find that there is an isomer of CS2, which is basically OOS, and it's linear. And it turns out that this has an energy minimum which is lower than what one usually may expect from a doubly charged CS2 molecules, mainly that it's bent there, okay? So there is an isomerization process going on, and then once it's in this, I don't know why this is flipping so much here now. I'm a little bit annoyed. Once it is in this geometry, then there is a way out there to where it can dissociate, and then where basically the sulfur atom separates from the O2 moiety. And in this way, the O2+ is formed. You can ask, why is this interesting? And that was then one of the things which we put in that paper, which appeared by the end of last year. It turns out that molecular oxygen is, of course, we know that, necessary for life, and is accumulated in the Earth's atmosphere since more than 2 billion years ago. And there are models out there which try to explain the origin of this, what is called the abiotic formation of molecular oxygen. Those common models, they primarily involve CO2 and water vapor, but they still can't explain the amount which is out there. So what we then suggested in this paper, and we also give a bit of a quantification in that paper, is that additional, and we even believe it's a significant contribution, may come from environments where SO2 is known to be actually around or in fairly large quantities, like for instance, in atmospheres, planetary atmospheres around Jupiter, like the moons Io, Europa, and so on there. I can talk, if someone is interested in this, I can talk about the actual sort of how we quantify this model. I can talk later on. Now, I want to move on a little bit and tell you what is one of the new directions which we do is actually work on. So far, we have worked a lot on stable molecules, which are easily accessible. But it turns out there is an even larger class of molecular systems, the so-called reactive intermediates, of which essentially nothing is known about the dicadionic electronic structures. Single ionization, single electron spectroscopy has been done by John Dike at Southampton, and then there's nice, beautiful work by Ingo Fischer in Würzburg, where he looked at the threshold electrons and the photoelectron created in single ionization in coincidence, but about the more highly charged electronic states, they are not known. And this is what we work on right now, and where we believe we can actually make a substantial contribution again. We have the first paper, a few papers out there. So this is one, HNCO. We as physicists could synthesize it, but what I'm really looking for are good people who can do chemical synthesis, because there are many more things we could like to do. And then, of course, you know, this is it's a demonstration that one can do it with this technique which we got there, and so from that we get the of course the double ionization energy, the lowest, and the triple ionization energy, and the full spectrum. With some calculations, we can then assign the states and so on. There was another system which one of my students worked on, is S2. This is actually even more challenging. The way we produce it is based on the vapor pressure of, so you use mercury sulfide, and you heat it up, and then S2 is formed. But life is not so simple, because it turns out that not only S2 is formed, but also S3, S4, and so on. So, and there it's really important to have the ion selectivity on hand, so that you get at the end of the day electron spectrum of the dication of S2. So you basically need to filter on the S2 double plus species in order to get then a clean spectrum. And this is actually also then was quite interesting to do that, because there was a paper out by, oh, sorry about this. No, there is a paper out by some, no, I'm getting annoyed, by some Ukrainian, where they tried to measure the lowest double ionization energy. First of all, they talk in this paper, is a bit strange. They call this the double ionization energy, but I think what they mean is the second ionization energy, which then, of course, if you add it to the first ionization energy, then gives you this value for the double ionization energy. But with our technique, we can actually show that it's somewhat higher. But if we accept what I say, the way we understand that paper, then they were not too far off. Anyhow, so I'm here a little bit to make to look for new people as well. And that would be one thing one could think about, a nice collaboration. First of all, some really hands-on people who can do nice synthesis, help us with the production of those reactive intermediates. And then also, once you have the data, we rely on collaboration with theoreticians. So if there is some interest in. And then I was thinking about, I show you just one beautiful picture. Remy has seen the environment. This is actually how it looks like about 500 meters away from where I live. It's a little boat harbor. And so if you happen to come to Sweden, it's right, you can see it's at the North Sea. It's right out here where I happen to live. And Gothenburg is, of course, at the west coast. Then there is my little son. If you come with your boat, you may start talking to him. Okay. Anyhow, this is just for fun. I want to go on to the second part, the time-resolved experiments. So, and there I will start first with, there is this stream at free electron lasers. This was one of the motivations to cast molecular movies, very similar to what Ahmed Sevai was, of course, onto. but just like SEY did this all with tabletop lasers, so a limited photon energy range, and by having access to the free electron lasers, you can actually now then access the valence electrons, ionize them, and also the core electrons. This is the beauty of the free electron lasers, right? So then there was one interesting experiment proposed by one of my senior colleagues, Maria Novella Piancastelli, also chemist by training. She had an interest in this acetylacetone, and this exists in basically two tautomers. One is called the enol, so where you basically have then that it's a ring, and the keto, where the one of the hydrogens has actually moved there. Okay. And it is known from a traditional electron spectroscopy paper made by those people in Australia that depending on the temperature of the system, so if you have it at room temperature, then it's mainly the enol form. If you heat up the sample, it turns into the keto form. And the dream was then to use a free electron laser where you can pump the system using the third harmonic of a titanium sapphire laser, pump it into an excited state, and then use the free electron laser, it's the Italian one called Fermi, 20 eV, to ionize the system, and then do this as a prompt delay. And that time, the spectrometer which we got there could detect ions or electrons. It was not already set up as a complete coincidence spectrometer. So what we then measured are, of course, the ions created as a function of the pump probe delay, and we see that many of the ions created, so for instance, a C3+, a C2+, CH+, and so on, they are actually, they show a substantial change in the yield within a few hundred femtoseconds, and basically above 2 picoseconds, the yields are stable. And then we also looked at the OH+, and this is the parent ion, the zinc ionized parent ion. And there we realized that those two species, their yield changes much slower. And in fact, that the OH+ has such a comparatively long time behavior that was already known by an experiment, of course, by Ahmed Zewail, done at that time in his lab. So this is very much in line with what they were doing. So now the question is, what is the new thing? We went on to electron detection, which Zewail couldn't really do at his time. And we were hunting for, this is again the valence photoelectron spectrum as measured by the Australians, now as a function of different time delays between the UV pump and the XUV probe. And we were hoping to see that if we warm up the system with the 261 nanometer UV pulse and probe it, that after a certain time delay, here a new peak would come up. This third peak, which would be the signature of this of the other tautomer. Yeah? But it didn't happen. What happened instead was that we got new features in the electron spectrum at higher electron kinetic energy or lower ionization energies. And this basically means this must be some sort of features related to excited states. And then, of course, the other thing is, if you look at it, they have different sorts of temporal behavior. So at that point, the experiment was certainly giving new results, but you need to have, again, theoretical support to get the explanation. And the theory results, which I will present shortly now, it was done by, I don't know if any of you know her, Nadia Doslik, a very, very good person to work with. And Aurora, she's actually working now with Fernando Martin in Madrid. And then Piero Di Cleva, of course, is very established and so on. The first thing is they made an assignment. They came up with an assignment for those 3 additional features which we saw there. The one which is at the lowest binding energy or the highest kinetic energy, this can then be explained in terms of a transition from an S2 pi star excited electronic state down to the first ionic state, which we then denote here as a denol. The second one, there is another electronic state. It's an N pi star excited state, the S1, and then it's a transition down to the first ionic state. And the third one can be related to a third state called the T1 state, which is also a pi star excited state going down to the D node. Then we analyzed the yields of those three features as a function of the pump probe delay. And we see, for instance, the feature explained in terms of the S2 state that has, again, a very short time delay there. It's very fast behavior. And the other two, they are a bit longer on a longer time scale there. And then to get this, of course, these are in they did the simulations, they get in their simulations very similar temporal behavior. And at the end of the day, what one can come up with, their theory is a very nice model. So you start off with the acetyl-acetone in the ground state, you do an excitation with the UV, you come onto this S2 state, the pi star excited state, and then it evolves, the system evolves along the potential energy surface of this S2 state. It comes out to a conical intersection where it then can actually go on to this S1 state, okay? So then it goes on to this S1 state, and once it is in the S1 state, there are basically three different pathways possible. And the conical intersection here is actually reached within 100 femtoseconds, which then actually explains why the transition from the S2 state down to the D null state is so fast, because it's basically, there things happen very quickly. But once it is in this S1 state, then there are, as I said, there are still three possibilities to go. And the dominant way will be to go through, it's basically, it goes on to the T1 state through another state, which is this T2 state here. And then after about 1 picosecond, 60% of all the trajectories have gone this way. And then the remaining ones, 15%, they will go another way. They will go this way onto the S, they go down onto the S node. And then there is the remaining trajectories, they stay trapped in the S1 state there. So this is what we got from this paper. It was, of course, not what we hoped for, to see the isomerization, but we got a lot of nice dynamic information there. So now I will come to the third part of the presentation. And this will be something which I call it's entirely new direction in Gothenburg, in the sense that here we actually go on to an even faster time scale experimentally than the femtoseconds. It will be about what I call real-time resolved experiments on the electron dynamics. So this is attosecond experiments. And for this, when I came to Gothenburg in 2014, and then I tried to get money for this project through the ERC. Twice I was at interviews, and they didn't get the money. And then I was on the thesis committee in Lund, at the Lund Laser Center, about very beautiful attosecond experiments. We had a nice person from the US as an opponent, Louis De Modo, and we started to talk. I had a very nice discussion. And at the end, we got the proposal right. So what this proposal is about is to do attosecond time resolved experiments on negative ions. And I explain you now how we want to do it. So I got in 2017 a large grant from the largest private foundation in Sweden called Wallenberg. And we decided then to set up a lab called, we call it Attohallen or the Attohall. And it starts with a construction. And I was naive when I wrote a proposal because I thought, okay, what do you need, right? But it turns out you need, when you buy a laser system and want to be able to operate it as a turnkey device, you need to have temperature stabilization of ±0.5 degree. And you need to keep the humidity level. So at the end, the faculty kicked in 450,000 euros to do this lab rebuild. And the total cost of the project is more than 6.5 million euros, which I think is probably the largest project for that department. It's a fairly small physics department. So lab space was built. Eventually, we had the pandemic. I was always crying because we couldn't, for some time, we couldn't actually do much there. But by the end of 2021, we finally could inaugurate this new laser lab. There are the laser tables here in the background. Now they are also equipped. There is a laser system. People have been using for a long time, for those femtosecond lasers, the titanium sapphire technology. And then this is based on what is called the CPA technology. Okay, so So chirp pulse amplification, the CPA stands for chirp pulse amplification. Now there is, I would say, even a revolution going on when it comes to the femtosecond lasers now. The OPCPA technology, which is a beautiful technology, optical parametric chirp pulse amplification, is a very strong technology. And we are happy that we first of all had the funding to get one. This is the first commercial system of the type which we got from a company in Eastern Europe. It's called Light Conversion, the company, and it's a beautiful laser which we got there. People, they were worried about when we would be putting our money into a new technology that we would need to be there every day and adjust it. And I have a very good laser scientist, but she tells me the only thing I do in the morning is I go in, I turn the key, it warms up, after half an hour, it works. And we get the pulse energy, and we're talking about high pulse energies here. So one of the arms, 50 millijoule on a daily basis without having to stand there for hours to optimize it. And this is because of the temperature stabilization and so on, which we achieved there. Now we want to build, at the end, we want to have something, I mean, it's called high harmonic generation, and I will try to explain this in a minute, how this works. At the end, we want to have basically two beamlines. With the high harmonics, we get an X-UV radiation out, which have properties to do attosecond experiments. And in order to get a very high pulse energy also for the X-UV pulses, we start off with 50 millijoules at a repetition rate of 100 hertz using an OPCPA using several OPCPA amplification stages, and then we have very short pulses below 10 femtoseconds. But we have to use a very long focal length to focus this laser radiation into a gas jet where the high harmonic generation process happens. Because otherwise, if we don't use this long focal length, it's for the optics, it's problematic. This is why this lab became so big. Okay, but at the end, we need to have, at the light matter interaction point, we need to have high harmonics, which have a high number of photons, because we want to blow off electrons from negative ions there. Then eventually, this is not there in place yet. This is in the design phase. There will be a second beamline operated at a much higher repetition rate, 10 kilohertz, and then of course the pulse energy, the laser pulse energy goes down, of course, and we can use much shorter focal lengths there. And then we have a third, I call it the auxiliary beam port, where we have on a daily basis available, of course, the fundamental, and then the fourth and the fifth harmonic is just we bought a harmonic modules, and this is actually used by one of the user groups already, because we want to operate this laser facility not only for our own purpose, but as a user facility where one can come with an own experiment. If you have an own experiment to set up an own detection system, we're happy to accept people and they come, or you just come with ideas. Use the equipment which we got there, have ideas, let me know, and we do something together. This is the idea, okay? So this is just how the laser looks like. It's this light conversion, and there is another, they are actually door-to-door, those two laser companies in Lithuania, and Expla. They put their brains together and they made this first commercial system. The technology has been developed for high laser power facilities in Europe. They are called extreme light infrastructures, ELI facilities. There are 3 of them. For that facilities, or for those facilities, that technology has been developed. As I say, this is the first system which has come on the market, but there will be a second one within short at Lund University. And I'm pretty sure more people will buy it. High harmonic generation. Some of you may know that, and I'm not the inventor of it at all. This has been, in fact, Anne Luyet, who is the one who runs the attosecond environment in Lund. She was, as a postdoc, they discovered the process of high harmonics. And the way it works is you have an oscillating laser field, you expose it to an atom, and because of the fact that the laser field is so strong, it changes the potential. Let's say in an atom now, bends it down, an electron can tunnel away, and then after a half cycle, it will get bent back and the electron will come back. So it's a kind of recollision process. And when the electron comes back, there is a certain probability that the energy which is basically then, I mean, when it comes back, it will be able to transfer energy in a certain form, and this energy can come out as XUV photons. So this is how you convert 800 nanometers, or let's say visible photon, to XUV photons there. Very nice. And then the nice thing is that this happens every half cycle. If you have a femtosecond laser where the pulse duration is more than, let's say, 10 femtoseconds or 20, then you will have several cycles. And those harmonics are created at each half cycle. And this is why you actually then get a pulse train. You get a train of attosecond pulses. And it leads to, if you detect it, it leads to a frequency comp. And those, and then there is a phase relation in those different harmonics, which is very important because it has a fixed phase relation. And what you then can do is you can put on top of the XUV an IR pulse. And then there is either you add an IR photon. So from here, you start with this harmonic 11, you add an IR photon, then you get to this state, or you subtract an IR photon from the harmonic 13, and then you reach a state here, which is basically in between those two features here. So this would be the ordinary photoelectrons coming created by one of the harmonics. And you, in between those two, you get something which is called a sideband. If you then vary the time delay between the IR and the XUV, the intensity of those sidebands, it will vary as a function of the time delay. And technically speaking, you can control this time delay with a precision which is below femtoseconds. So it's on the attosecond time scale. You do it with on a micrometer scale, technically speaking, with those delay stages there. Then what you can do is you can analyze how the intensity of the sidebands, how it varies as a function of your tau, the time delay. And it turns out formally, it will give an oscillation. It's a cosine function there. And then there are different contributions. One is, of course, the actual, the physical time delay, which you introduced there, but then there is a grouped contribution, a contribution due to the group delay of the attosecond pulses. And the third one is what is then what can be related to the Wigner time delay, which is basically the time it takes for the electrons to leave the system. So this is on a, what we want to have at the end of the day there. Now we've done with the Lund people, we supported them in doing it, these sorts of experiments on neon atoms. It's a nice paper in Science, which we got out there. But I want to explain you why I think it would be even better to do those experiments on negative ions. So if we start off with negative ions, of course, this is, many people here know the beauty of negative ions. They exist because the additional electron is bound by electron correlation, right? So, and if we now go back to this equation, which I have shown you on the tau I, basically the Wigner contribution, it turns out that it has two contributions. One, which is the physical time delay it takes for the electron to leave the system, but then there is also an artificial contribution introduced by the IR field because of the fact that if you take off an electron from a neutral system, you will create an ionic core. And how much this contribution is, it's not easy to measure at all. So the idea is to start off not with a neutral system, but to start off with a negative ion. Because if you blow off the electron from a negative ion, what remains is a neutral system. And then this contribution here, it should be, I should be careful in saying it will go away entirely, but it will not, of course, not go away entirely, but it will be basically negligible, okay? This is what we want to do, and we hope to be able to do the first experiments on F- and chlorine-, but can be others. We think that it would be very interesting to measure F- because then we can compare it directly to the known attosecond experiments on neon, and the chlorine- would be isoelectronic to argon. That would be the start. And then I have quite some interest in molecular anions, and I have some dream about doubly charged molecular anions, dianions. This was why I was asking earlier today about these nice isos which you got down there, because there you could even examine then the if you take the 2 electrons off of a doubly charged negative ion, then you would be able to measure the electron correlation part in a very beautifully time-resolved way. That's the dream. So now where are we with the experiment? To do this, you need to combine 3 things basically. You need to have this a high power laser and doing the high harmonics. To analyze then 2 electrons, if we eventually want to do the double detachment, you need to have a correlation method and you need to have the negatively charged ions. So we need to combine this, and it's not trivial. Many of you will be able to appreciate those experimental challenges here, because of course the ion target density, there is a limit to it. It's the space charge. And in order to compensate this, you need to come up with a light source which will have an intensity so that at the end of the day, you get a reasonable detachment cross-section there. And this is why we have to go, this is something called a microscopic power scaling law. In the high harmonic generation process, you can go to a long focal length. And the idea is then you basically, when you have a gas jet where you create the harmonics by using a long focal length, you will be able to create the harmonics in more atomic species than if you use just a very short focal length. And then eventually for the molecular anions, we want to cool them vibrationally and these sorts of things. And the other thing is also there is Doppler effect, of course, which will have then, if the anions move too fast into a spectrometer, you will have a Doppler contribution and the resolution will be affected by that. So one has to think about is how to do this. This is now how the laser facility looks like today. So the high harmonic generation part, these are enormous dimensions. Is a laser table which is more than 10 meters long, and we do this very long focal thing. And then we have at the other end, so somewhere here up there is the gas jet for creating the harmonics. Down here we have an XUV spectrometer just record the high harmonics, and this is what we then achieved last year. So this is actually 2022 in spring. This was the very first high harmonic light which we saw just on a CCD camera. And then, of course, we use the dispersive spectrometer to get the high harmonic spectrum of xenon. So we use xenon for the high harmonic generation, then argon. And this has improved a lot because there are many parameters you need to fine tune. This is now the latest results. We had a number of bachelor students helping in the lab. And this is what I arrived at in March. There is an interferometer to do the controlled way, control the time delay between the XUV and the IR. And the way you do it, I have a very talented optics engineer. So we use what is called hollow mirrors. And the idea is that an XUV beam and an IR beam, they have 2 different divergences. IR is much more divergent than the XUV. So you use a mirror which has a little hole. Then the 2 beams, they arrive, they are collinearly. You send them onto that hollow mirror, and then you actually split it off in a way that the central part, which is the XUV, will go through this mirror, and then the IR part will be reflected on the outside of where the hole is, and it goes onto a second set of mirrors. And then what you do is you fine control on a micrometer scale the two paths, you change the distance between those 2 sets of mirrors, and this way you get the attosecond time control. Okay, and then you reflect them back onto another hollow mirror and recombine them, because then they want to go into the interaction region of the spectrometer, again in a collinear geometry, but with time delay, a relative time delay between them. And then we need to have an electron spectrometer, and we love to build those spectrometers. So this is actually another spectrometer which formally will not belong to our activities, but we build it for one of those extreme light infrastructures in Europe, ELI in the Czech Republic. We helped them building it, and it's commissioned, and we actually use the spectrometer now also to commission our beamline because it was just there. And this is then a photoelectron spectrum where we had the XUV and the IR on top of each other. There you get, first of all, photoelectron peaks, which are due to the different harmonics in the high harmonic comp. But then you clearly also see that we have those side bands. And this is, of course, a very big step now towards doing the final thing, namely finding the time zero and then controlling the time delay between the IR and the XUV. And then we need to have one more component. These are the negative ions. Okay, and this, we first tried to develop a negative ion setups ourselves. I had a postdoc who did lots of simulations and so on. But then eventually I learned about a company in, they are in Athens, called, oh, no, let's go back. It's called Phasmatech. And it turns out that they can make an apparatus for us within the budget given. And they are actually very good in making ion setups based on an ion source using the electrospray technique. But we will then be able to also hook up another ion source, which we got there already. But then basically, you know, you need to have an octopole ion guide or some sort of ion guide, a mass filter, which is here. And then because of the molecular anions, we will need to cool them. So there will be a cryocooler. We want to have the molecular anions in the lowest vibration state. And then it will go into the spectrometer. And this is a challenge in itself. How do you actually get those ions in a good way into, this is just a cesium sputter ion source, which I got from the US. This is Nora Barra's stuff. But yeah, we will make use of it. Now let's go back. Just go back one step here. No, this is the wrong direction. So to get the anions into our electron spectrometer, the magnetic bottle, why is it doing like this? Into the magnetic bottle, then we will basically use the same trick as I learned as a postdoc, but just the other way around. Instead of sucking cations in this direction, we will bring the anions through a hollow magnet in this way, and then it comes to the light matter interaction, and then there we will do the experiments. And this is actually also turns out this is a way known in the literature when it comes to, there is a whole community which uses magnetic bottles for doing electron detachment experiments on anions, and this is from one way of doing it basically. I will finish off by giving just 2 minutes by saying that one of the users groups comes actually from Groningen now, and they make use of the auxiliary beam port where we have the fundamental and the fourth and the fifth harmonic. This is the group of Thomas Schlathölder. And this is also how we actually get trained on, you know, using an ion setup. So they have, of course, their ion mobility spectrometer, and they were willing to come with it, and it's now in our lab, and it will be there for a good while. I got a network grant through the faculty, which is one way of getting actually money for having people there for a while. So I have a network grant to have those people there for some periods during a total period of 2 years. And what they want to do is, Thomas Schlathölder is very much interested in DNA G quadruplexes, so very large systems, which are then also very easily produced by the electrospray technique. He has an ion trap. So what we did now so far is basically, they came along with this spectrometer, we found the overlap in their trap, and then, this is annoying. And we then had to find the time zero between the IR and the fourth harmonic. This is where we are with this, and they will come back again. So now we have the time zero, and this is a femtosecond experiment, which will continue by the end of this month and into the middle of July, and then we will see. I will stop here. There would be more to say about the future, but I will just skip this. We can have that for a discussion later on. But I should be very clear on that none of that what I have shown you would have been possible without having a number of talented people. And I have been during my career, I have been lucky, first of all, at the beginning, that I always found supportive people who trained myself, but then also that I actually have been lucky in finding lots of good students, but also postdocs. And then some of the postdocs which I had, they eventually became, he's a research engineer now. And Helene, she's the laser scientist. She is now a senior researcher at our department. John Eland from Oxford, my postdoc advisor. We still are in close contacts, and he's made the honorary doctor at Uppsala University. So was you, right? And sometimes I have guest professors. This is, of course, the laser people at Lund University are important, and then the ion part. There's Thomas Stadtholder, but I'm also in contact with Lai Sheng Wang, for instance, at the Brown University, a very enthusiastic person. Nora Barra, she's not doing so much on negative ions at the moment. And then I was early on working with someone, I don't know if how well he is known here, but Dieter Gerlich in Germany, he was one of the first ion trappers. And it's so sad because he came to me before the pandemic. We started to work together. And then in October 2020, I was notified that he passed away, not because of the pandemic, but he was hiking and got a heart attack, and then he didn't get an ambulance into the mountains, of course. So he unfortunately passed away. But he was one of the original people to work with. So just a photograph. I keep saying at the moment, this is Richard and this is Elaine, my two big stars when it comes to the laser project. Thank you very much for your attention, and if there are questions. Yes, yes, yes.
I remember later that it was the second yellow star in the middle. She was here.
Yes.
She came here. In the same program.
Yeah. Exactly. Yeah. So yes, yes. And she actually told me to say hello to you and you guys. Yes, this is actually what she told me when I left. Because I think she has very nice memories of me.
I hope so.
Yeah, oh, she does. Yes, she does.
Okay.
Okay.
We open the session for questions before we get hungry and we go for lunch. Questions?
Yes.
Questions. Okay. Ladies first.
Thank you so much for your nice talk. My question is about the high harmonic generation. I think when you apply a time-dependent laser field, then you don't have the conservation of the energy. You have quasi conservation of the energy. Did you take this point into the account?
In which respect? I mean, what when you say take it into account?
I mean, when we apply a time-dependent laser field, we don't have the conservation of energy anymore.
Right.
And we have a quasi conservation of energy. We must take the time lag very small.
Okay.
Did you consider it?
We haven't considered. I mean, we just take this technology from what other people have been developed. So I don't think I'll be able to comment on this more deeply. But I mean, it works beautifully. I mean, if you want to, you start off with visible photon, and then you want to go into the XUV. This is what you do. And because of the harmonics they have a specific fixed phase relation, you get a very nice timing tool on the attosecond scale. This is
so all of them was experimental. You didn't make a theoretical part in this.
No. Okay. Yeah.
Okay. Thank you.
Sure.
Well, thank you so much for your talk. Very nice. Just looking at double ionization, I kind of stopped thinking about reality effects. Have you ever considered looking at those things? Because I assume your photons are polarized, right?
They usually linear polarized.
Linearly.
Yeah.
But have you considered looking at clarity effects?
No, we haven't, and we wouldn't be able to do that with the spectrometer which we got there, because this is some spectrometer which is basically integrating over the whole 4 pi solid angle. Okay, but there are, I know there are other people. There was quite some, and there still is actually quite some interest in that. So there is a group in Frankfurt run by Reinhard Dörner. You may know him from the ALS. They have a big program going on, the chirality of molecules. And they have the means to look into, because they have a coincidence setup which is optimized for angular distributions. This is their big field. Okay? Yes. Thomas?
Yeah, thank you very much. Very nice talk, very impressive work. I have a rather basic question as I do theory. I'm always yeah, impressed to see the measurements you do, and then let's say photo emissions spectra for a certain molecule, but at the end you measure some resonances, and then I can imagine a lot of processes which could take place there. You mentioned these Auger processes, so many things can happen.
Yes.
And how do you end up with identifying these resonances with a certain process? Do you need first, do you make lots of theoretical models, or how do you?
So when it comes to the Augers, this is actually a fairly easy process to distinguish from many others. Because it's a sequential process. The photoelectron comes out with a specific energy, and then the Auger electrons comes out with a specific energy. So the two have very well-defined energies. You look at the cross correlation of those two, and I give lie basically to a little spot on the coincidence map. And then the direct process, there the electrons share the two. They share arbitrarily the energy. They will give rise to a continuous background. So in this way, we can experimentally fairly easily distinguish the two different mechanisms there. But this is not always possible. So, but when it comes to the Auger, there we are very certain. But very often, and I need to be clear on this, we have sometimes experimental data where there is room for several processes, then we rely on theory. And we need to do the modeling and see how well the modeling fits, and maybe improve the model in a certain direction until we got a good fit. In relation to the experimental data.
Okay, thank you very much.
Yes.
Any other question? No.
I find it really amazing to realize how good is doing the Sigvan Swedish school in molecular photoionization.
Okay, thank you.
After years, you know. Well, probably a very small question. You know, you show is really amazing.
Okay, thank you.
Could you please tell me the difference in the knockout, shake off, shake off, which I don't know if it's the same.
So the knockout is actually, you can understand it in a sort of classical picture. Photon gets absorbed. One electron takes up basically the photon energy. Essentially, it starts leaving the system, and then on the way out, it will collide with a second electron. And then this is basically elastic collision process, and they share the energy arbitrarily. This is also why in that, I don't know how fast I can go back to in this slide. This also basically means, if you look at, I had this sort of 2 electron energy sharing curves for different excess energies. If the excess energy is low, it's basically flat, and this tells us that it's basically knockout there. So now the shake up, what is that? So the shake up is basically, again, photon gets absorbed, and an electron with fairly high kinetic energy leaves the system, and then there will be a reorganization going on in the remaining, among the remaining electrons. And then there is a probability that a second electron will be basically shaken off, quantum mechanically probability, and this second electron will come off with a much lower energy. This is why then the energy distribution gets so U-shaped. And then by looking at how the distribution change as a function of the excess energy, you clearly see how it goes from the knockout to essentially the shake off.
Shake off and shake off. I saw before.
Yeah. So this is, I was talking about the shake. This is a shake off, but then there are also those shake up processes which we have not been looking here. So shake off is basically one electron goes out to have a reorganization, and the second electron comes, is basically shaken up or shaken off. Yeah, exactly. So it's like, you know, could call it maybe organization or shape. Yeah.
Any other question? Okay, I have a last one. In the last part that you talk about the future of this nice and wonderful experimental setup that I have been lucky enough to walk outside with the corridor. I never thought that you had that experiment in there.
The next time when you come, I'll show you.
How can Is it possible for you that they're moving from femtoseconds to attoseconds, not only to measure the delay time of the experiment, but to create the movie of the process?
Yeah.
Is it possible for you to do that?
Oh yeah, sure. This is essentially, I mean, what we will be. I think this will be one possibility in the future. And the other thing is, I think the really interesting development will be eventually. People are doing experiment already on molecules. But if you create, so you remove an electron from a molecule, then you will have created, of course, a vacancy there, and the charge will migrate. And there is a very nice prediction by Lorenz Sederbaum on what he calls purely electron correlation driven charge migration. To see that in real life, that will be beautiful.
Okay, yeah,
Yes.
that would be beautiful.
Yeah, but there are, I mean, this is a big dream, and I have a colleague in Lund, Jonsson is his name. This is his big dream. He has been trying this for 10 years. It's not easy, and there are groups in Germany. We will see how we get there. But it could be that perhaps it may turn out that it might be a very good experiment on negative ions.
Okay, so we'll see.
Yeah, we'll see.
Well, let's thank Professor Feifel for this wonderful experimental talk.
Thank
with
you
a
very much for
connection of
having
a
me.
lot of groups and a lot of setups. And as I already mentioned to here, one of the students, there is possibility to interact with him experimentally. If you are interested in the future, just pay attention to the University of Gothenburg webpage. So with that, let's thank Professor Feifel for this wonderful talk.
Thank you so much.
Yes.
Or you just send me an email. That's even better. If someone has any sort of interest, I'm happy to answer.
Yeah.
Okay. Thank you.
Thank you.
Thank you.